All right, welcome back. I'm not sure this light situation is much better than it was before, but maybe it'll be less distracting to you than it is to me. Um, let's hope so. All right, so in this video, we're going to be talking about the goodness of fit test. All right, so unlike all previous tests, we do not start with a hypothesis about population parameters. Remember, we're no longer doing a parametric test, so it makes sense we wouldn't start from population parameters. Instead, our null hypothesis in a goodness of fit test is going to be about proportions, all right? In other words, what percentage of people do X or Y? What proportion of people do X or Y? All right. So, for example, do more people like Pepsi or Coke? Maybe 55% of people like Coke better, and maybe 45% of people like Pepsi better. That's one of the possibilities of a proportion of people, okay? So we're not thinking about a parameter like a mean or a correlation. Instead, we're just thinking, what's the proportion? All right, so here, our null hypothesis could be 50%, 50%, all right? Remember, our original null hypothesis that we've been working with all semester is basically no effect, right? No effect. And so here, you're basically saying they're the same, all right? This is called an equal proportions null hypothesis, meaning people don't prefer Pepsi or Coke. That's our null hypothesis, all right? Another way we could do this is if you've got multiple groups, instead of doing a 50-50 split, you would do a 1/3, 1/3, 1/3 split. Oh, geez. All right. Now, the second type of null hypothesis is you could do the same as a known population, all right? So for example, if you know from previous research that men make up 80% of engineering majors, and you want to know if ELAC is different, all right? Then your null hypothesis here would not be 50-50 men versus women. Instead, it would be 80% and 20%, or maybe it would be like 4 out of 5, 1 out of 5. Okay? So these work the same way. Now, in either of these cases, the alternative hypothesis is just anything besides that. All right? For up here, the null hypothesis would be people don't have no preference. They do prefer either Coke or Pepsi. Or on this side, they do prefer red, white, or blue, all right? In the second type of hypothesis test, you're just saying 80-20 is wrong, all right? Maybe it's actually 70% male and 30% female, or maybe it's actually 90% male and only 10% female. All you're saying is it's not that, okay? So let's start off with an example. Are the proportions of male and female psychology majors at ELAC similar to those of the whole country? All right. For the whole country, women make up 66.7% of psychology majors. Now, I kind of fudged that a little bit, but it's pretty close to that. All right. To do this test, we're going to use my previous class as an example to test this hypothesis. I originally wanted to use our class, but the numbers are a little bit wild. So I thought this previous class was a little bit better, okay? So we have a sample size of 12. And our first step is we're going to check out our null hypothesis, all right? Now, what do you think our null hypothesis is here? We're trying to ask, are the proportions of male and female psychology majors at ELAC similar to those of the whole country? So what should our null hypothesis be? Okay. Now, if the proportions in the whole country are 66.7% female, then that should basically be our null hypothesis. All right, so we predict that we'll have 33.3% males and 66.7% females. Now, step 2 is we're going to calculate our expected frequencies given our sample size, okay? What that means is we're going to take these null hypothesis predictions and we're going to say, okay, under the null hypothesis, if we expect to get 66.7% females, then how many females should we get if we've got a sample of size 12? All right, so there were 12 people in the class. If the null hypothesis is correct, how many should be women and how many should be men? All right, in fact, I want you to try this on your own. Go ahead and pause the video. If you already have it, then don't pause the video. But if you don't have it yet, pause the video, try and figure out how many males do we expect to find, all right? That's what we mean by expected frequencies. Frequency is the number of people, and expected means, based on the null hypothesis, how many do we expect to get? Okay, so what we're going to do here is we're going to figure out the number of participants we expect in each category, all right? Now, how might we find this? Or maybe, how did you find it? Right? Now, what we're actually going to do here is we're going to simply multiply the null hypothesis by our sample size, all right, by our n. So our null hypothesis values are 33.3 and 66.7. So to get our expected frequencies, we're going to do 33.3%, which is the same thing as 0.333, multiplied by 12. All right, so that's basically the same thing as saying 1/3 of 12, which is 4. All right, so we expect to find 4 males. Then we can do the same thing for females, 0.667 times 12, and that's 8, 2/3 of 12. All right, so 0.333 times 12 and 0.667 times 12. All right, great. So we've got our expected frequencies. That means if ELAC students are just like all students in the country in terms of psychology, male and female breakdown, then we should expect to get about 4 males and 8 females in our study. Maybe not exactly 4 and 8, but it should be close to that. All right. Now, it is important to note, like I sort of talked about earlier, these will not always be whole numbers. In fact, they usually will not be whole numbers. And so in our class, for example, we've got 16 students, which makes it nearly impossible to get this to work out in a pretty way, okay? So don't expect these to be whole numbers all the time. So we did step 2. We calculated our expected frequencies, all right? Next, we have to calculate our observed frequencies. Now, to observe something is to watch it happen. So what observed frequencies means is just what we saw, what we collected, all right? And in the case of my previous class, we only had 1 male and 11 females. So not exactly the same as those expected frequencies and really not super close, all right? But we're going to have to use statistics to figure out, is it far enough that we think ELAC students are different from students across the whole country? All right. So step 4 is going to be to calculate our chi-square. All right. Now, hopefully you've noticed chi-square is our what? We first started with Z, then we have T, F, R, and finally chi-square. All right. So it's our 5th statistic, all right? So what we're going to be doing here is we're going to be asking, how well do our observed data reflect the null hypothesis? And what we'll do to test this is we'll use this formula, all right? So let's look at this formula. Over here, FO is observed frequencies, okay? So that little squiggly F, it's an italic F, stands for frequency, and the O tells us we want the observed frequency. And then we're subtracting that from the expected frequency, okay? So what we expect to find. So that's just gonna be how far apart are the two values, all right? Then we're going to square that and make all of these values positive, all right? So much like F, all of the values we add together here are just gonna stay on the positive side. We're not gonna deal with negatives in the chi-squared test. Then, after we've added up after we found the difference between the observed frequency and the expected frequency, then we square that difference, and finally, we divide it by the expected value, okay? And the last thing that we have to do is simply repeat that process as many times as we have to for all our categories. In this case, we only have male and female as our categories. All right, so let's give it a shot. We have to calculate our chi-square. Here is our formula, and let's give it a try. And in fact, I think it might be a good idea for you to pause here, try it on your own. We're going to get another example of this in a bit in the next video. So if you don't want to try that on your own, it's all right. We can wait till the next one. So we start with our observed frequency, 1, minus our expected frequency, 4. So clearly here on this first one, I'm doing males. And then divide it by our expected frequency again. So 4. Then, because we're doing the sum of all of those, we're going to have to do the same thing again, but this time for females. So our observed frequency is 11 minus our expected frequency of 8, again squared, divided by our expected frequency again, 8. 1 minus 4 is -3, squared is 9, 9 over 4, plus 11 minus 8 is 3 again, squared is 9 again, over 8. All right. Now, when you only have two groups, these are always going to be the same on the top, all right? Because there's only two groups, so however many one is off by, the other one is going to be off in the opposite direction, which is why we had -3 on the left over here and then +3 on the right. But the squaring makes it so that doesn't really matter anyway, okay? So 9 over 4 plus 9 over 8. Now I'm going to convert that to 18 over 8. Just double the top and the bottom of that fraction. Plus 9 over 8 equals 27 over 8. Okay? And there is our chi-squared value. That's what? 3.375? Nice. 3.375. Okay? Great, so we found our chi-squared value. Step 5 is to compare that chi-squared value to our critical value, all right? And in order to do that, we're gonna need a chi-squared table. But before we get there, let's talk just for a bit about the chi-squared distribution. Now, the chi-squared distribution is actually gonna look very similar to the F distribution, all right? It starts at 0, has a big hump in the beginning, and then teeters off toward the end. All the values are positive, so we only have to deal with 1/2 of the data. And the distribution has a positive skew, which means the tail points to the positive side, okay? So, what if our observed frequencies are exactly the same as our expected frequencies? So our expected frequencies in this case were 4 and 8. So what if our observed frequencies were also 4 and 8? We happen to have exactly 4 males in our class. Well, when we calculate our chi-squared, we would get a really low number. How low? Well, our observed frequency for males is 4, minus 4, our expected frequency. So that's 0 squared is also 0. And it doesn't matter what's on the bottom because that's 0. Plus 8 for our observed frequency for females minus 8. I think you might get where I'm going here. It's just a big fat 0. Okay, so if we get exactly the same scores that we were expecting, we're going to say, yeah, this seems totally reasonable from a population that looks just like the known population. Now, importantly, also like a F distribution, the shape of this distribution is going to depend on the number of categories. But it works a little bit differently than it did in the past, all right? And the reason it works differently is because when you've got more categories, when you increase the number of categories, that increases the number of things that you're adding together for that chi-squared value. Because remember, for chi-squared, you're taking the sum of a bunch of numbers. So the more numbers there are that you're adding, in other words, the more categories you have, the bigger your chi-squared is going to be just sort of naturally, all right? And so because of that, we have to increase our critical values to match that. So if you've got additional categories, we're going to need higher critical values for you to hit for us to believe that it's actually different from the null hypothesis, okay? So with that all being said, our degrees of freedom are based on the number of categories we have, not the number of participants. So number of participants doesn't matter here. What actually matters is number of categories, because that's what affects our chi-squared values, okay? So our formula for our degrees of freedom for a chi-squared is, again, pretty similar to the formulas we've been using before. In this case, instead of being n minus 1, because we don't care about participants, right? We care about the number of categories. So C represents the number of categories minus 1, okay? So if we have more categories, then we'll have a more spread out chi-squared distribution, okay? So let's get back to our example. Remember, are the portions of male and female psychology majors similar to those of the whole country? All right. So we got our null hypothesis. We calculated our expected frequencies. We calculated our observed frequencies. We calculated our chi-squared. Last, we have to compare our chi-squared value to a critical value. Okay. So we've got our chi-squared. Next, we need our degrees of freedom. In this case, C minus 1 is the number of categories we have, male and female. So 2 minus 1 is just 1, okay? So our degrees of freedom is 1. So we have to go find our chi-squared critical value, all right? And in fact, before I do it, you've used a lot of tables now. I want to see if you can try it on your own. Try and figure out what our chi-squared critical value is before I do, all right? All right, so here we've got our chi-squared distribution, and at the top it says the area to the right of the critical value, okay? So I want us to think about what that might mean. Now, here is our chi-squared distribution, got 0 right there, and there's our approximate distribution, okay? And so they're saying the area to the right of the critical value. Now, I don't know what that critical value is, but they're asking us for the area to the right, or rather they want to give us a certain amount of area to the right. And remember, that's basically the area where it's possible to get that even if the null hypothesis is true, but it's unlikely, all right? Just like we remember when we were thinking about a z-test, all right? When we found a score particularly far away from the mean, that would indicate to us that it's pretty unlikely that score came from the null hypothesis. Now, it's not impossible, but the chances are very small. How small? 5%, okay? And the reason we know that is because we had 2.5% over here and 2.5% over here, okay? So in our chi-squared, when they ask us what area we want in the right of the critical value, the area we want is 5% of the total. So that's right here, 0.05. Because remember, 5% is the same thing as 0.05, okay? So we have 0.05 and 1 degree of freedom. So our critical value is 3.841. All right, so now we've got our chi-squared value, we've got our chi-squared critical value, and we're ready to make a decision. Okay, so our chi-squared value is not as extreme as the critical value. So there's no reason to think that our population that our sample comes from, ELAC, is any different from that of the whole country, okay? If they were very different, then we would have expected to see a critical value, or rather a chi-squared value, more extreme than our critical value, okay? That would tell us they were very different from each other. But our observed frequencies and our expected frequencies were not that different, okay? All right, so that's all for video 2. We introduced the goodness of fit test. We talked about 2 different types of null hypotheses. One was equal proportions, where we just put an even number of expected frequency in each group, or we compare it to a known population. That's the one that we worked on, okay? The known population said 66.7% women, and so we use that as our null hypothesis. Then we talked about expected frequencies and observed frequencies. Expected are the ones we expect to find if the null hypothesis was true. And our observed frequencies are the frequencies that we actually found, okay? So next time we're gonna run through an example and you'll get another opportunity to try this out on your own, all right? I'll see you then.